Hey folks, welcome back. In this video we're going to go over question 1 from the 2023 SQA National 5 Physics exam paper, so let's get started. Question 1 says a seagull flies above a school playground. The seagull remains at constant height above the ground during its flight. Part A says the seagull flies from point A to point E following the route shown. So it goes 38 metres from A to B, 74 metres from B to C, 14 metres from C to D, and then 11 metres from D to E. Part 1 says by scale diagram or otherwise determine the magnitude of the resultant displacement of the seagull from point A to point E, and there's 2 marks available here. Well, we want to use either the scale diagram or calculation method here, and I'm going to use the calculation method. Now looking back at our diagram, I'm going to draw a sketch so that we have a right angled triangle in order to do the calculation method and use Pythagoras. And on our sketch, our hypotenuse is going to be the resultant displacement vector, which goes from the starting point to the finishing point. So it's point A to point E. So that means we can join 2 displacement vectors from nose to tail, going from here to here to here, and then our resultant from A to E. So starting at A, we have our first displacement vector going up to this point here, and that's going to be 24 metres in length, and we can label that as A. The reason I know that's 24 metres is because this full length from A to B was 38 metres, and remember this distance over here was 14 metres. So if I do 38 minus 14, I get this leftover distance here. So that's 24 metres. And our second displacement vector will go from this point to point E here, which is going to be 63 metres in length, and we can label that B. And again, I know that's 63 metres in length because this full length from B to C is 74 metres. This little distance here is 11 metres, so doing 74 take away 11 gives us 63 metres. And then we can draw a resultant vector going from A to E, put a double arrow on that to show it's the resultant, and that makes it different from the single vectors. And then we can label that side C. And we can then put a right angle in there and our angle theta next to the starting point. So now we have a right angled triangle we can use for this question. So let's just redraw the triangle on its own so it looks a bit clearer. And we can then use Pythagoras to find this unknown side C. So we have c squared equals a squared plus b squared, substituting in the numbers gives 24 squared plus 63 squared, and put that into your calculator should give you an answer of 4,545, and then to find c we want to take the square root of both sides, so we get c is equal to 67 metres. Part 2 says by scale diagram or otherwise determine the direction of the resultant displacement of the seagull from point A to point E, and again there's 2 marks available here. Well, again we can use either the scale diagram or calculation method, and I'm going to continue using the calculation method for consistency. And remember, to find the direction we first want to calculate the angle theta, which always uses tan. So we have tan theta equals opposite over adjacent, where the opposite side is 63 metres and the adjacent side is 24 metres. So we have 63 divided by 24, and then to find theta we can do inverse tan or shift tan in your calculator of 63 divided by 24, and that should give you an answer for theta of 69 degrees. Now that we have that angle, we can use either compass points or bearings to define the direction. So using compass points first of all, remember this direction over here would be west, this would be north up here, so our resultant vector is between north and west, so we could define the angle first of all as 69 degrees west of north. Or if you wanted to use bearings, remember we always go to the starting point and think about north, the bearing of 0, 0, 0. Of course, going from here all the way around back to the start would be 360 degrees. So in order to get from here all the way around to here, we just need to do 360 take away this angle here. So if we do 360 take away this angle here of 69 degrees, we get 291. So we could also define the direction as a bearing of 291. Part B says the seagull takes 31 seconds to travel from point A to point E. Part 1 says determine the average velocity of the seagull for this journey, and there's 3 marks available here. Well, writing down what we know from the question, we're trying to calculate the average velocity v bar. We know the resultant displacement from part A there is 67 metres, and the time t is 31 seconds. So writing down our equation relating average velocity, displacement and time, we have s equals v bar t. Substituting in the numbers gives 67 equals v bar times 31, and to get v bar on its own we need to divide both sides by 31, so putting that into your calculator should give you an answer for v bar of 2.2 metres per second, and because this was average velocity, remember velocity is a vector, so we need a direction there as well. So we need to state either 69 degrees west of north, or you could state 2.2 metres per second at a bearing of 291. Those were our 2 directions that we just found in A part 2. B part 2 says a student states that the average speed of the seagull between point A and point E is greater than the magnitude of the average velocity of the seagull between point A and point E. Explain why the student is correct, and there's 2 marks available here. Well, first of all, we could say the distance travelled is greater than the displacement. So remember the resultant displacement was only 67 metres compared to the very big distance travelled from the initial diagram. And we can also say the same time is used to calculate both average speed and average velocity. So if we have the same time for both calculations, and the average speed calculation uses a bigger value for distance, then we're going to get a greater average speed value than if we used the displacement value of 67 meters. Or another way you could do this is to show it by calculation instead. So you could plug in the numbers to the two equations to show that it's going to be greater for the average speed rather than the average velocity. Part C says the seagull now flies at a height of 7.5 meters above the ground, holding a chip in its beak. The mass of the chip is 0.0025 kilograms. Part 1 says show that the gravitational potential energy of the chip at this height is 0.18 joules, and there's 2 marks given for this. Well, writing down what we know from the question, we're trying to calculate the potential energy EP. We know the mass of the chip is 0.0025 kilograms, the gravitational field strength G on Earth is 9.8 newtons per kilogram, and lastly the height h of the chip is 7.5 meters, because the chip is in the seagull's beak, so it must also be at 7.5 meters initially. Now writing down our equation for gravitational potential energy, we have EP equals mgh. Substituting in the numbers gives 0.0025 times 9.8 times 7.5, and putting that into your calculator should give you an answer of 0.18 joules, as expected. C part 2 says the seagull now drops the chip. Determine the maximum vertical speed of the chip as it reaches the ground, and there's 3 marks available here. Well, we could answer this in terms of conservation of energy. If you think about the chip to begin with, it's got that gravitational potential energy, but as the chip falls, it's going to gain kinetic energy. So eventually all of that gravitational potential energy is going to be converted into kinetic energy, assuming no energy losses. So we could say by conservation of energy, assuming the air resistance is negligible, we have that the loss in gravitational potential energy EP is equal to the gain in kinetic energy EK. So here we're trying to find the maximum vertical speed, which is the final speed V. We know the mass m is 0.0025 kilograms for the chip. We know the kinetic energy we just worked out is 0.18 joules. And this is us saying that the kinetic energy is equal to the gravitational potential energy that we just calculated in part 1. So writing down our equation for kinetic energy, we have EK equals a half mv squared. Substituting in the numbers gives us 0.18 equals a half times 0.0025 times v squared. And then to get v squared on its own, you could times both sides by 2 to get rid of the half here, and then divide both sides by 0.0025, and that should give you v squared equals 144, and then to get v on its own you want to square root both sides, so doing the square root of 144 in your calculator should give you an answer of 12 meters per second for v. Lastly, C part 3 says explain why in practice the vertical speed of the chip as it reaches the ground is less than determined in C part 2, and there's 1 mark available here. Well, quite simply we could say the energy is lost as heat due to air resistance or friction. You wouldn't have to state both of these, just one of them to get the mark. So remember we assumed the air resistance was negligible for our calculations, but in reality that's not going to be the case. Energy is going to be lost due to air resistance or friction. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.